Hello again. In this R session, we are going to learn about solution of questions related to spatial discrete random variables, such as binomial random variable and the Poisson random variable. Of course, a programming language can be useful if the calculation of the probability is too complex for these random variables. But in order to learn these built-in functions which will be helpful to calculate these probabilities, we are going to start with simple applications which can easily be calculated directly by using a formulation and a calculator. However, for practical, for learning purposes, we would like to use the programming language here. So let's just say the capital X random variable is here is a binomial random variable with size parameter n and success probability p. In the theoretical lecture, we have learned that the probability mass function for this random variable is n choose x times p to the power x times 1 minus p to the power n minus x. And this probability mass function is only valid for integer values from 0 to the size parameter n. Remember, the binomial random variable represents the number of successes occurring in a repetition of n independent Bernoulli trials, each of which has a success probability p. Now, let's just say somebody asks you the probability of a binomial random variable being equal to 2, and that size parameter of this binomial random variable will be equal to 5, and the success probability will be equal to 3. So I'm very sorry for this misprint here. This value should be equal to 5 instead of 2 here. So we are looking for a size parameter 5 and success probability 0.3, and we are looking for the probability of our binomial random variable being equal to 2. That is calculated by the Binom function, which helps us to calculate the probability mass function for the binomial random variable. And you are basically asking us the probability mass function at 2 when the size parameter is equal to 5 and the success probability is equal to 0.3. Now, if you just copy this comment and R, it will calculate you these binomial random variables probability mass value at 2. Basically, what I am trying to calculate here, the probability of x being equal to 2, where x is a binomial random variable with size parameter equal to 5 and success probability equal to 0.3. Okay. Now, we can also use this function to calculate another probability mass function for another binomial random variable. So let's just say we have a binomial random variable with size parameter 15 and success probability 0.8. Let's just say the probability to score at a penalty shot is 0.8 independently at each trial, and we are taking 15 penalty shots. What is the probability of these 10 of these 15 penalty shots to be exactly a success? Now you can calculate that probability again by the Binom function. Binom function. The first argument that you need to introduce is the value in the probability of interest. So we are looking for the probability of exactly 10 penalty shots to be scored. Now the total number of trials is 15, and finally the success probability at each trial is 0.8. Now you get this probability in this example. Right, so in another example here, we have a binomial random variable with size parameter 4, and the success probability at each trial is 0.5. So what are the possible values of this random variable? We can have no success, exactly 1 success, exactly 2 successes, exactly 3 successes, or all of them can be returned in a success. So this time, the function is trying to calculate the probability mass values for all of these values one by one. So what you are going to do is this time, you are going to use the Binom function again, but this time, the first argument will not just be a single value. Instead, you are going to introduce a vector of values from 0 to 4, and it will calculate the probability mass values at each of these points, assuming that the size parameter is equal to 4 and success probability is equal to 0.5. Now, if you start this integer vector from -2, and if you end at, let's just say 9, now you will see, you would get the probability mass values for -2 and -1 as 0. And also you would get the probability mass values for 5, 6, 7, 8, and 9 as 0, because the probability mass function is defined as 0 at these points, as you can see. Okay. So basically, we can calculate the probability mass values in a binomial distribution, all of them in a single command line, by this practical approach. It is also possible to calculate the cumulative distribution function. Remember, the cumulative distribution function is defined as the probability of a random variable to be less than or equal to x, which is the summation of probabilities, the positive probability masses up to that point. So let's just say you have a sequence of Bernoulli trials. You are just going to repeat the experiment for 5 times, and at each experiment, the success probability is equal to 0.4. What is the probability that at most 2 of them will be a success? At most 2 of them will be a success. Now that is the probability of capital X to be less than or equal to 2. Okay, the probability of at most 2 of them to be success. So this is basically the probability of our random variable to be at least equal to less than or equal to 2. Okay, so at most equal to 2. Now, the cumulative probabilities for a binomial random variable is calculated with P-binom function. Instead of D-binom, it is calculated by P-binom. And P-binom 2 with size parameter 5 and success probability 0.3, it is calculating us the probability of this binomial random variable to be equal to be less than or equal to 2. Okay, so let's write that. So this time, the next command line is interested in calculating the random variable, binomial random variable, to be less than or equal to 2, where this binomial random variable, x, has size parameter equal to 5 and success probability equal to 0.2. Again, I am very sorry. There is a misprint here. It shouldn't be 0.4. It should be 0.3 actually. All right. So how we are going to calculate this probability? This time we are using P-binom and writing all probabilities less than or equal to 2 will be included here with size parameter 5 and success probability 0.3. And that value is 0.83692. Now, let us calculate each of probability mass values starting from 0 to 2, which includes 0, 1, and 2 here. Again, under size parameter 5 and success probability 0.3, and these 3 values are here. If you sum these 3 values up, you would exactly get the cumulative probability for 2. So this cumulative probability includes the probability masses at 0, 1, and 2, because all of these 3 values are less than or equal to 2. In fact, you can calculate this cumulative probability by using the summation of the probability mass values from 0 to 2, again using the D-binom function, as we have learned above. Now, let's just say this time, instead of the probability mass values from 0 to 4 for a binomial random variable with size parameter 4 and success probability 0.5, this time we would like to calculate the cumulative probabilities. Okay, so the cumulative probability at 2, for example, which is the probability of this random variable to be less than or equal to 2, is including all these 3 probability mass values, because 0, 1, and 2 are less than or equal to 2. Now, for that, we are just going to repeat this above example, but this time we are just going to write P-binom. If you compare with the above values, these are the probability mass values at each point. But these are the cumulative probabilities up to that point. So you see, what is the probability of our random variable to be less than or equal to 3? It is 0.9375. In fact, this can be calculated as the summation of these 4 values. Okay. Now, if you just use that Binomial function and if you use the cumulative sum function, the vector's cumulative sum will be calculated, which is exactly the same as the Binomial function. So Binomial function calculates the less than or equal to probabilities for binomial random variables, and Binomial function calculates the exact probabilities, exactly equation probabilities for each of these values. Now let's just solve a practical question. For an exhibit, 100 tickets are sold, and each guest is likely to miss the exhibit with 3% chance independently. Now, in this experiment, we are repeating basically a Bernoulli experiment 100 times. Now, if we consider for any guest to miss the exhibit as a success, and the success probability will be equal to 0.03. So anybody misses with 0.03 probability. So there are 100 experiments here, and the success probability for miss is 0.03. Now the question here asks, calculate the probability of exactly 5 guests to miss the exhibit, or exactly 6 guests to miss the exhibit, or 7 guests to miss the exhibit. So we are going to calculate the exact probabilities for each of them. So what we can do is we can just calculate the binom for all values from 5 to 7, where the size parameter is 100 and the success probability is 0.03. So this is the result of the first part of the question. So it says, find the probability that no more than 4 guests will miss the exhibit. No more than 4 guests. So this is basically asking us the probability of x being less than or equal to 4. Because no more than 4 guests will miss the exhibit, it says. Now that probability is basically P binom at 4 under size parameter 100 and success probability 0. I'm sorry, not this one. This one. Yes. So this is the probability of no more than 4 guests to miss the exhibit. And in the last part, in the third part, it asks, find the probability that at least 10 guests miss the exhibit. At least 10 guests, which means in this part, the probability of x being greater than or equal to 10 is being asked. So at least 10 people will miss the exhibit. This means this binomial random variable x will be greater than or equal to 10. And that is 1 minus cumulative probability. Remember now, 10 is included in the above inequality. So if we are going to subtract the cumulative probability, we need to subtract the cumulative probability at 9 for this discrete random variable, because 10 will be included in the answer. So 1 minus the cumulative probability at 9 for size parameter 100 and success probability 0.03 will be subtracted from 1. And that is the result that you are looking for. The probability that at least 10 people will miss the exhibit out of 100 invitations is a very small probability, 0.0009 approximately. Finally, the question asks us to calculate the probability for at least 2, but at most 7 guests to miss the exhibit. At least 2, but at most 7 guests to miss the exhibit. So the question here is asking the probability of 2 being less than or equal to x being less than or equal to 7. So the question is asking us this probability. Now, how are we going to calculate that? We are going to calculate the cumulative probability at 7 first, and from that we will subtract the cumulative probability at 1 because 2 is included in the probability statement. And this is just helping us to calculate the probability of x being between 2 and 7 values. Or you could have used the Binomial function from 2 to 7 and sum these probability density values up. I'm sorry, probability mass values up. Still, you would get the same result, okay, in both ways. Finally, in this last question, we are going to use the programming language R to draw the probability mass functions. So it says, for a binomial random variable with size parameter 10 and success probability 0.2, draw the probability mass function. So we know that this binomial random variable can take any value from 0 to 10. From 0 to 10. So we can calculate the probability mass values for each of them. So let's just say x is a vector of integers. X is a vector of integers from 0 to 10. And we can calculate the probability mass values for a binomial random variable here for all values from 0 to 10. And the size parameter will be equal to 10 and the success probability will be equal to 2. And this command then calculates all of these probabilities. So all we need to do is we need to plot this x vector versus the probability mass values for a binomial random variable. X and 0.2 here. Now you see we have the probability mass function. Now the probability mass value at 0 is 0.10 approximately. The probability mass value at 1 is 0.27, it is around here. The probability mass value at 2 is 0.3 approximately, which is here. So we have the plot diagram here. Now let's just change the plot character. So PCH means plot character to 19. If you do that, the 19th character will be a black dot. Okay. Now this is a number that is a label for the black dot. Of course, you wouldn't know that. It is not very easy to understand that, but that 19 stands for the label for the black dot. Now, if you change this to 18, for example, you would get a different sign. Instead of a black dot, you would just get a diamond shape here. Now, if you change it to, for example, 15, you would get a square. Okay, so 19 stands for the black dot. And you see the probability mass function for this binomial random variable looks like this, which means if you repeat a Bernoulli trial 10 times independently, at each trial the success probability is 0.2. Now, the probability that having none of them as a success is 0.10 approximately. Exactly one success has the probability of 0.27 approximately. Exactly two successes has probability of 0.30 approximately. Having exactly 3 or 4 successes you are seeing that the probabilities are reducing here. In fact, the probability of observing exactly 6, 7, 8, 9, or 10 successes are very small probabilities compared to the other ones. So according to this probability mass function, it is less likely to observe a smaller value for this binomial random variable. In fact, the expected value of this binomial random variable is 2, okay, 10 times 0.2. So this is how we draw the probability mass function for a binomial random variable. Let's just practice it for another binomial random variable. This time, x is just going to be a binomial random variable with size parameter 20 and success probability 0.7. And we would like to draw the probability mass function here. So what I'm going to do is this. I'm just going to take this x as 0 to 20. So there will be 20 trials. 0 of them can be a success, or at most 20 of them can be a success, but a few of them can also be a success. What I am going to do is to plot this diagram again. This time size parameter will be 20 and the success probability will be 0.7. Now the expected value for this binomial random variable is of course 14. So it is a large likely to observe a large number of successes this time compared to the failures. And the probability mass function will look like this. Now this is exactly the plot diagram that we are seeing here. Okay. So we are just going to continue our applications in the next video.